All right, we are in unit number 4, Force in Motion, and I'll be lecturing in this video on page 8, which will cover the weight equation. We'll do example number 6 and example number 7. So here we go. The weight equation. Let me kind of zoom in just a little bit. The other day, our previous lecture, we talked about Newton's second law, and we defined Newton's second law as F equals ma. All right, we know that. That's Newton's second law. But we'd like to give you I'd like to right now give you a related equation. We know that your weight is a force. And it's a force that's due to the acceleration of gravity. And so what we're going to do is we're going to sharpen this equation up just a little bit, and we're going to make it real specific. We're going to do it specifically for the weight. So instead of this being just a real generic force or a real generic net force, we're going to call it weight, W. Not work, but weight. This is m, that's your mass. And this a, instead of it being a generic acceleration, we're going to call it the acceleration of gravity. And this is your weight equation. So we're going to record weight under force on your dimensions and unit sheet. So if you want to stop the video and go find your dimensions and unit sheet, I would highly recommend it. And then we'll fill some stuff in here because we got a little bit to do yet on it. So put where you see weight, right on that put force. I'm sorry, where you see force, put weight on your dimensions and unit sheet. Because weight is classified as a force. And the governing equation, you can say W equals mg. The weight equation, which is what we have right here, the weight equation is just another way of representing Newton's second law. That's all it is. Both equations can be used to convert between mass, force, or more specifically weight, and mass. And that's the value of this. Remind me and I'll show you this brain quest transparency in class. All right, let's move on and do something specific. So let's do example number 6 and see if we can work through this one. So calculate your mass in kilograms and in slugs if 1 Newton, and here's the number that's nice to have, if 1 Newton is 0.225 pounds, which can be found in the front cover of your textbook. So those of you that can actually find your textbook, it's in there, front cover. All right, so my weight right now is about 163 pounds. I'm going to convert that from pounds to newtons. So here's the conversion. So 0.225 pounds is 1 Newton. And if I do that on my calculator, 163 divided by 0.225, I get 724 newtons. So the next time you go to your doctor, next time you go to the doctors and they ask you what's your weight, just look at them and say 724 and see what the reaction was, because you're not lying. Your weight really is 724. It's just 724 newtons. You know, if they look at you weird, you say, well, you got to be specific. You got to specify the units that you want your answer in. Well, if you want pounds, I'll give you pounds. If not, I'll give you anything I want. 724 newtons, it is. All right, now, that's not our mass. We want our mass in kilograms and slugs. So we're going to do kilograms first. So we'll do W equals mg. And we want mass, so mass is W over g. So weight is 724 newtons divided by gravity, and the acceleration of gravity is 9.8. And if we divide those out, so divide by 9.8, I get 73.9. And that'll be, now what is that going to be measured in? look at what you got. A Newton is going to be a kilogram meter per second squared all over meter per second squared. Do you see how all those units cancel out and the only thing you're left with is kilograms? And there it is. There's your mass in kilograms, 73.9 kilograms. All right, the next one. We want your weight in pounds. And this is where it gets to be a little goofy. So let's solve for weight, or solve for your mass. My weight, now I'm going to use pounds on this, is 163 pounds divided by the acceleration of gravity. In this case, I've got to use the acceleration of gravity measured in feet per second squared, because remember the other day we talked about a pound, and a pound was going to be a slug foot per second squared, and all that's divided by your feet per second squared, and all that cancels out, and you're left with a slug. So how about I divide those numbers out first? So 63 divided by 163 divided by 32 gives me right at about 5 slugs. So your mass is either 73.9 kilograms or 5 slugs. And now that we did that, I'll tell you what the conversion is between these two guys. So actually, you can figure it out. It's pretty kind of cool. So if you just take 73.9, clear this off, and you divide it by 5, that'll give you the conversion. So it's about 17 point, depending on where I rounded here, it's really accurately about 17.59. I'm sorry, 14.59. I don't know what this was all about here, so we'll skip over him. Okay, the next one. We want to calculate your weight in pounds on the moon and in pounds on Pluto. So we want weight. So we'll just use the weight equation. W equals mg. Weight. Okay, I just looked up my mass. It's 5 slugs times the acceleration of gravity on the moon. Now, we know it's 1/6 of the Earth. So the Earth we know is 32 feet per second squared. I gotta use feet now because I'm using slugs and I want my answer in pounds. And I divide it by 6 because it's 1/6. So if I do 5 times 32, divide by 6, let's see if I can squeeze all that in here. There we go. So 5 times 32, divide by 6, I get 26.7. So that's my weight. If I stepped on a scale on the moon, I would weigh 26.7 pounds. Wouldn't that be great? Wouldn't look any different, because what you look like, remember, is your mass. Okay, the next one on Pluto. We're using the same equations, so we'll say W equals mg. Grab a different pencil. My mass, 5 slugs from above, times, now, here's the acceleration of gravity on Pluto. The acceleration of gravity on Pluto is about 0.96 feet per second squared, about a foot per second squared. On Earth, it's 32. On Pluto, about 1, about 9.96. So if I multiply those two together, so times 5, I get about 4.8. So if I step on a scale on Pluto, my weight would be 4.8 pounds. Wouldn't that be great? Wouldn't look any different, though. Keep that in mind. All right, the next one. Calculate the weight in newtons and pounds of a 1 kilogram mass. All right, so the weight. So we want weight is equal to mg. We're going to do 1 kilogram. Now, when I use kilograms, I got to go back and use 9.8. I got to use meters per second. I can do that math in my head. That's going to be 9.8 newtons. So if I have 1 kilogram is 9.8 newtons. Now, they want it in pounds as well. So I'm going to use the conversion I had above, 1 newton. I'm sorry, 9.8 newtons. And I know from above, right here, 1 newton is 0.225 pounds. if I multiply that through, this will work better. I get 2.2. Alright, so 1 kilogram is 9.8 newtons and 2.2 pounds. And here's my analogy. Zoom out. I have right here a liter. There's a liter of water. It says, if you can read it, 1 liter right there. Okay? 1 liter of water right here. Okay? Just a heads up, is 1 kilogram of mass. This is just a nice thing to know. 9.8 newtons, about 10 newtons, and 2.2 pounds. So 1 liter of water, about 2.2 pounds, 10 newtons, and 1 kilogram. That's a liter of water. That's nice to know. Alright, and the inside front cover of your textbook, so here's your textbook, the thing you guys never bring, has all of those conversions, and they're right here. So 1 newton is 0.225 pounds, 1 pound is 4.45 newtons, and then 1 kilogram on the Earth's surface is 2.2 pounds and 9.8 newtons. And there it is. Alright, next one. Key concepts, next page. Okay, when do I use negative 9.8? When do I use positive 9.8? It's pretty important we get this straight. We use negative 9.8 when we're doing the big three. Anytime you use the big three, it's negative. When we do Newton's third law, or sorry, Newton's second law, 9.8 is positive, and that's going to be in this example that we're going to do next. So example number 7 is pretty much our first example using Newton's second law, and this is a powerful law, and so need to make sure and take this in and make sure you get this one straight. So important that you catch this early, because we're going to be using Newton's second law all year long. And here's the first whack at it. All right, here's the question. When a 300 Newton force acting at an angle of 20 degrees to the horizontal is applied to a 75 kilogram box, the box slides on a level floor, opposed by a force of kinetic friction of 120 newtons. What is the magnitude of the normal force and the acceleration of the box? Begin with a free body diagram. Okay, that's a lot. So we're going to try to break that down and show you how we'll solve the problem. Alright, and we're going to break it down by drawing a diagram. So here's our diagram. Whew, that was a horrible line. Alright, there's the diagram. And there's our box. Alright, they say it's 75 kilograms. 75 kilograms is a scalar. It's not a vector. It doesn't go with an arrow. You don't put an arrow with 75 kilograms. So we're going to put 75 right here in the middle with no arrow because it's a scalar. All right. Next question I want to ask is, what forces are acting on this? What pushes or pulls are acting on this? And maybe a first one you're going to think about, well, you know what? They said somebody's tugging on this. It says when a 300 Newton force acting at 30 degrees or 20 degrees. So that's being tugged. So we're going to show that one. And so there's that guy. And that I guess you can think of this force as being applied to the box. And so we're going to call it FA. It's 300 newtons, that it is, and its angle is 20 degrees to the horizontal. So there's the first one. All right, what's the next one? There's actually 3 other forces. The next force is weight. Gravity's pulling down on it, and there's weight. And sometimes we'll call that FG, the force of gravity. They also talked about friction, this kinetic friction business, 120 newtons. Friction is always going to oppose motion. So if the object is moving to the right, friction is going to act to the left. So we're going to say F of F, friction, and they said it's 120 newtons. All right, the last force is the ground. The ground is pushing up on that box. Now we don't know how much it is, but we're going to give it a name, and we call it Fn. That's your normal force. So the ground is pushing up in a box. Remember in class we talked about me when I talked. When I was teaching in Springfield, and I I wanted to illustrate the fact, well, I called one of the smallest boys up to the front, smallest boy freshman, and I held him in my arms and I said, okay, is gravity pulling down on you? And they said, yeah. Am I putting up on you? Yeah. Because if I let go of you, you'd fall. Well, and I remember I said I laid him on the table. I said, is the table pushing up on him? He said, yes. If he's standing on the ground, is the ground pushing up on him? And that's yes. So the ground is pushing up on this box, and we call that force that the ground supplies. We call that a normal force. It's perpendicular, always perpendicular to the ground. Okay, now that we've got the forces, the next step is to use Newton's second law and answer the question. And this is going to be new. It's going to be totally different, so you kind of have to hang in here with me. So we're going to sum up. This is Newton's second law. F equals ma, and we're going to do it twice. We're going to do it once in the x direction and once in the y direction. So here's the x direction, and here's the y direction. Think of it almost like two parties. This is a party where all the x's get together, and it's a party where all the y's get together. All right, I'm going to focus on the y direction first. I'm going to focus on the x direction first. So here's the x direction. You need to know what this means right here. What does that mean? If you can get that, you're halfway home. This means that you have to list all the forces that are acting in the x direction. All the forces that are acting in the x direction. And so my question for you is which forces, or how many forces, are acting in the x direction? So you use your diagram. Well, this one's in a y direction. This one's in a y direction. This one's in the x direction. And this one's kind of maybe a little bit of both. It's a little bit x and a little bit y. So I kind of have two forces. This one and some of this one. And I'm going to list them right over here. I'm going to list them. I've got two forces. I'll put one right here and one right there. So here it is. The first one is f of f. And since it's going to the left, I'm going to put a negative. The second one is the FA. But it's the FA in the x direction. It's this component right here. FA in the x direction. All right. From this equation, I'm going to get the acceleration. So I'm going to solve this equation for FAX, because that's one of the things they wanted us to find was the acceleration. And that's going to be negative f of f plus FAX all over m. Alright, I'm going to zoom in just a little bit more so you can see it. So AX is equal to, well, do I know any of these things? Well, I know the force of friction. The force of friction is 120 newtons. I get that. It's not a problem. So I have a number for that. But I don't have a number for f of a in the x direction. I don't have this number. So I need to rename that number, almost give it a nickname. And we've done this before. If you look at this triangle, isn't this side next to the angle? And doesn't next to, or the adjacent, go with cosine? So isn't this AX really H cosine theta? And isn't H your f of a? Now, I will say this. You have to resist. I mean, some of you are thinking, well, hey, I know what 300 is. I know what FA is. It's 300. I'll just plug in 300. Now, resist that temptation. Trust me on this. Don't substitute the stuff in. So I'm going to substitute. I got negative f of f plus, now instead of writing FAX, I'm going to write what FAX is. Its nickname, you could think of it as FA cosine theta all over m. All right, now, do I know f of x? I'm sorry, do I know f of f? Yeah, it's 120. Do I know f of a? Yeah, it's 300. Do I know the angle? Yeah, it's 20. Do I know the mass? Yeah, it's 75. I know everything. Now that I know everything, I can plug it all in. So a of x is equal to force of friction was 120 newtons plus FA is 300 newtons, cosine of 20 degrees, all divided by the mass, which is 75 kilograms. And if I plug all that in, I'll see if I can do that for you. All right, so I'm gonna go ahead and start right over here and do 300 cosine 20. All right, that gives me 281. I'm gonna subtract off the 120, and it's in the numerator, and then divide that by 75. So my answer is 2.15, and the units for that is meters per second squared. All right, next one. Fy. All right, Fy, this guy right here, sigma Fy, is asking you to list all the forces in the x direction. List all the forces in the x direction. Well, let's see what you got. We've got the normal. I'm sorry, I said that wrong. List all the forces in the y direction. So we've got one here, got the normal. We got the weight, and we also have this component right here. And that component is also, so I really have 3 of them in the y direction. I'm going to list them. So here's the first one, second one, and third one. First one I'll say is normal. Since it's up, it's positive. I'm going to kind of draw a squiggly line here just to separate the 2 portions of this. Weight is down, so I'm going to go minus W. This guy's up, so he's positive, but he's the y component, so I'm going to put a y here of the applied force. Zoom in so you can see it now. All right, the next part. We need to figure out what the acceleration is in the y direction. Acceleration here, and this is kind of a tough thing. But think of it this way. The box is moving this direction. Is it moving in the y direction? I mean, do you see that the box is only moving sideways? It's not moving vertically. And if it's not moving vertically, then the acceleration in the vertical direction is 0. I'll say it one more time. If it's not moving in the vertical direction, then the acceleration in the vertical direction, or the acceleration in the y direction, is 0. So I can come back over here and I can say that that side becomes 0 because the acceleration in the vertical direction is 0. All right, so back over here. We want the normal force. That was the question. Well, look where normal force shows up. It shows up right here. So I'm going to move this guy and this guy to the other side. So there's the normal force. If I move this guy to the other side, he becomes positive. If I move this guy to the other side, he becomes negative. All right, now, I don't have a name for the weight. I mean, I don't have a number. Let me say it that way. I don't have a number for the weight, and I don't have a number for the force, the applied force in the y direction. I don't have that number, so I need to give them nicknames, rewrite them, rename them. Well, I have an equation for weight. We did it earlier in this video. The equation for weight is simply mass times gravity. And we have an expression for this guy. If I go back to my diagram, this guy right here is the applied force in the y direction. He's opposite, and if he's opposite, he's going to be h, not cosine, but sine. You got to be able to see it. So then the hypotenuse, which is right here, is FA. Again, don't substitute the numbers in yet. I know you're like itching to do that. So I'm going to substitute FA sine theta in for this guy. So it's negative FA sine theta. And if I just go through my list, I know the mass, I know G, I know FA, that's 300, and I know the angle. So I know everything. It's just a matter of plugging it all in. So now you get to plug it in. So the mass is going to be 75 kilograms. G is 9.8. Remember, it's positive when you're doing Newton's second law. This is all Newton's second law. Minus FA is 300. And then sine of 20 degrees. And I'll plug all that in for you. So I'm going to do the 75 times 9.8 first, get that number. And then I'm going to subtract 300 sine of 20. And there it is. 632 newtons. And there it is. All right, let's fill in all these these blanks down here, and then we'll be done with the video. All right, a free body diagram. What we just did right here is a free body diagram. Physicists love free body diagrams. We're going to do them all year long. So we're going to kind of sharpen this up a little bit, make sure you understand what they're doing. So here it is. A free body diagram is a diagram that indicates any and all forces acting on one object. What was our object up here? It was this crate, or this box. The next one. Free body diagrams do not include forces produced by the object in question. So we don't want to know the forces produced by the object or by the box. We only want to know forces acting on the box. All right, we talked about normal force. Normal force is a force produced by a surface that acts on an object perpendicular to the surface. Now don't forget to include it in your free body diagram. It's important. So that's this guy right here. That's the normal force. Easy to forget. The other thing we can't forget is don't forget to include friction. And friction is a force that always opposes motion. And I don't know if oppose has 1p or 2p. 2p's. And here's the big rule of thumb. This is a big one. If a problem doesn't indicate friction, then you can neglect the force of friction in a free body diagram. So if they don't say friction's in the problem, don't add it. Only include friction in the problem if they come out and tell you specifically that friction is included in the problem. There's the video. We'll see you tomorrow.